Okay, so today what we're going to do is work on applying the rational root theorem to find the roots of our polynomial. If you think back to what we did in 3a, we created a table where you filled out a lot of information about your function, and one of the very first things was this box here, which was the zeros or the x-intercepts. And on that day, we were able to factor everything, and then we were able to complete the table. But the second line here, it mentioned that another way to find your zeros was the rational root theorem. So certainly if your function is factorable, we're going to do that and be done. But if not, we need another way to possibly find the roots. Let's not forget, though, that we also have the quadratic formula that works for any quadratic. So you'll be seeing how that all ties in. So let's answer a few questions and then we'll do a couple of examples. So the rational root theorem, why is that important? And I hope that as I'm going through these, you're trying to answer these questions before I do. But the rational root theorem is important because it gives us a method of finding other roots when it's not factorable. Because we just wish everything could be factored, but it can't. Okay. And so what the rational root theorem does is we have to pay attention to the words. It doesn't give us all the roots. It gives us the rational roots. So those are ones that are going to be whole numbers or can be written as a fraction. Your irrational roots will not show up here, but remember that they're going to give us real roots that are rational. So the theorem was going to drive us finding all those possibilities and seeing which ones work. That doesn't mean that there aren't other types of roots, and we're going to talk about that. Okay, so this is just one step in finding the other methods, or the other roots, I'm sorry. What is our overall goal and our goal while we're applying the roots? So our overall goal is to identify rational roots. And by doing so, we are able to then hopefully find other roots. And because our overall goal is to, well, I put that in reverse. So our overall goal is to find all the rational roots. But while we're applying it, our goal is to reduce the equation, or the equation down to a quadratic. Because if we can use the quadratic formula, that's going to help us identify the real irrational as well as the imaginary roots. So this is a goal that while we're using the root theorem, we want to get down to a quadratic, but in the end, we're trying to find at least the rational roots, if not more. All right. Now, if you remember, we've learned how to synthetically divide, and the goal of that was because we needed it to apply the rational root theorem. How do we know if we synthetically divide and we get a root? We have a root when the remainder is 0. So we like to do the bobblehead dance when the remainder is 0. And if it's not 0, then what we have just found is a point on that function. And that's valuable information if you're trying to graph a function or understand its behavior. Now, when you synthetically divide, you get the remainder of 0. We just said that's a root. It's also going to be a factor. So if, for example, we were to if we were to divide by x equals 2 and we get a remainder of 0, then we know that x equals 2 is a root, and we know that x minus 2 is a factor. And it's important to realize it tells you both of those. And so it also tells us that 2, 0 is a point on the graph or on the function. And as we do that and we get a remainder of 0, or even if we don't, if we're writing factors, each time you divide, the power reduces by 1, and that's because you're dividing by a binomial with power of 1 on the x. So anything divided by x to the first would reduce it down 1. So now we're not going to write it as that unless we get a remainder of 0. You can write it as factors of products, but we tend to not write it anymore with the remainder of 0. Now, a couple special things about the roots, and don't forget that you can also have duplicate roots. If there is an imaginary roots, they always come in pairs. And that's because they're found through the quadratic formula, and the imaginary is going to come out of that plus or minus the square root. If we have a negative in the square root, it's going to give us an imaginary number plus or minus. So it's always going to be in pairs. So if you know you're looking for 5 roots and you know a pair of them is, or that you know you have an imaginary root, if you have 1, you have 2. So if you need 5, 2 of them are imaginary, so now we're only looking for 3 of them. And we don't usually know until the end whether or not they're imaginary. If there's irrational roots, they can also be found through the quadratic formula. So something like plus or minus the square root of 7. That's going to give you the irrational part of your quadratic formula. You can also use completing the square and those types of things, but we'll probably use quadratic formula the most. And if there are rational roots, they will be found through the rational root theorem, which we're working on today. Or you can do factoring, which we would love to do every time. Or you can use the quadratic formula that's already mentioned. You technically might be able to apply completing the squares if it's low enough. But we hope factoring will work. If not, we try the rational root theorem so that we can get to the quadratic. Sometimes it's nice to ask, well, which numbers should I even try in the process? And there is Descartes, who is a historical person. If you ever study the history of mathematics, he had a lot to do with the development of mathematics. And he came up with what's called Descartes' rule of signs. And what this is telling us is how many positive answers are we going to have and how many negative answers. And that includes all real roots. So what we do, and we're going to do this in just a second, but we're going to look at the number of times the sign changes in either the original function or f of negative x. And if the sign changes in f of x, it will tell us, for example, we might have 3 positive roots, and so 3 positive roots could either be 3 positive roots or 1 positive root. So it's always going to decrease by an even number. Because the reason it's always going to decrease by an even number is because the imaginary numbers come in pairs. So if it's not real, it's imaginary, and imaginary comes in 2s. So if I think I either have 3 positive answers or something, I can't have 2 positive answers because they're real, the imaginaries come in pairs. So 3 or 1 positive answers. So we'll see how that works in just a minute in our example. Likewise, number 9 here is just a full kind of list of everything. Oops, I went too far. A full kind of list of everything we want to do as we go through the rational root theorem. So we're going to identify the p's and the q's. Remember, p is the constant and q is the leading coefficient. And as we find all possible factors, don't forget it's plus or minus. Both of those might work. Then we're going to get the ratio of p over q, and again, narrow the list down by reducing, that type of thing. Then we're going to dive in And if you're working with partners, it's good to say, okay, I'll try this, you try that. And whoever finds one first, you both need to get on the same page there and go to the next step together. But don't forget your positive negatives. You will start to get better at getting a gut feeling of what to try, but sometimes it's pure just luck. And once we know that we have a root, we want to write it as a root. We also want to keep track of it as a factor. If you do find the root, then you're at that point going to reduce your function that you're working on by that power of 1. If it's not a root, remember that gives you a point on the graph. All right, and in the end, we want to be able to both write our answer as a product of factors, as well as we want to be able to write it as the roots of the equation. Once we find the roots, and so all we're doing, if you think back to your document 3A, this is a snapshot of 3A. All we're doing on 3A is this right here. And once you find your roots, you can then go back to that whole table in 3A and identify every part of the graph. Okay, so this is just handling the finding of the roots. Now, the very first question I want to do is one that we did back in 3A. It happened to be factorable. So I want us to know the answers before we start on this one, but I'm going to force us to go the wrong way a couple of times on purpose so that we're not just using the answers that we know are there. So the first way it's presented is this is actually factorable, but I'm going to expand it a little bit. And remember that x squared minus 4 really did need to be factored to x plus 2 and x minus 2. So you can see that we have 4 factors, which means we have 4 roots, and we could solve each of these. We have some duplicate roots there and so on. So this does give us the answers that x equals 1, x equals negative 2, and x equals 2. So keep in mind that's what we're hoping for, but let's see how it all works. So the polynomial below is the exact same polynomial, but all multiplied together. So first, let's look at our p's and q's. Remember, your p is your 12 and your q is your negative 3. And so the factors of p would be equal to, so anything that multiplies to give us 12. So it would be plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, and plus or minus 12. And I really do encourage you to hit pause at many points in this and try to do this yourself as you're able. And the factors of q, which is negative 3, would be plus or minus 1 and plus or minus 3. Now, to find any possible rational roots, so if it's a rational root, it's going to be in this list. We're going to take every number in p and we're going to put it over, so any number in that yellow, and we're going to put it over every number in this green. And what I like to do is I like to take every number in the top and put it over the 1 in the bottom, and then I'll do every number on top with the 3. If we already have something listed, we don't have to list it again. So first I'm going to take all the p's, which are in yellow, and I'm going to put them over the number 1, which means I'm getting the exact same list. 1 over 1 is 1, 2 over 1 is 2, 3 over 1 is 3, and so on. Now we have to take the yellow list and put it over 3. When we do, again, if it's already listed, we don't have to include it. So we put 1 over 3, which is plus or minus 1 over 3. We put 2 over 3, which is plus or minus 2 over 3. We put 3 over 3, which is 1. 4 over 3, which is plus or minus 4 over 3. 6 over 3 is 2, which we already have, and 12 over 3 is 4, which we already have. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9 times 2 because of the plus or minus. We have 18 different rational roots. And hopefully we don't have to try them all. Now in this case again, this was factorable, and we're not going to torture ourselves if we can factor. But I do want you to see how the process works knowing the answers already. Now let's find out whether we should focus on finding the positives or the negative numbers using the positive or negative p's over q's. So let's check for the number of possible positive real roots. To do that, we need our original function, and now what we're going to do is we are going to count the sign changes of the coefficients. So here we go negative to positive, which is 1. Then we go positive to positive, which is not a change. We go positive to negative, that's another change. And we do negative to positive, which is another change. So we have 3 sign changes for positive roots. And remember, imaginaries come in pairs. So either we have 3 positive roots or 1 positive root. And we can't go down lower than 1 because we'd go into the negatives. So what that guarantees us here is that at least one of our answers is positive, but as many as 3 of them could be positive. Okay, so we are guaranteed one of our answers is a positive real number. And what we hope is that it comes from one of those in the list. Now let's check our negative. As we do negative, think about what we're really doing is everywhere we see an x, we're putting a negative 1x. And as we do that, you have to just think about what the power would do to that negative. So this time I'm going to write it out. We don't always write it out because we hope we can say, well, this is going to square it, which is going to not change it. So, but then don't forget you're multiplying it here and then plus 12. So if we clean this up, the negative to the 4th power just makes it a positive, so that doesn't change anything. But here the negative x to the 3rd is going to give me a negative 6x cubed. That's again a negative 1 there. Negative x squared is just going to make it positive, so 9x squared. A negative times a negative here is going to give me a 24x plus 12. Now we're going to talk about sign changes in this. We go from negative to negative, which is not a sign change. We go from negative to positive, which is a sign change, and then positive to positive to positive. So no additional sign changes. This then, so we have 1 sign change, and it can't be reduced by 2 because it then would be a negative answer. This guarantees 1 negative real root. 1 negative real root. Okay. So we know that we are looking for 4 answers because of x to the 4th. And of those 4 answers, we know 1 is positive and 1 is negative real. So we know it's going to hit our x-intercept at least twice, and that the other 2 can either be positive or they can be imaginary. Okay, so we have a feel for what we're looking for. Oops. Let me see, my computer's doing something all by itself there. There we go. Let me get back here. All right, so now let's dive in and see which of these roots might show. Well, I'm going to, and I just for no reason, not because we already know an answer, but I'm going to set up my synthetic division. And we're going to use the coefficients of our function in order. Oops. And because it's first on my list, and because I know I have a positive, I am going to try 1. And there's no special reason to try 1 over anything else. So recall, we're going to bring down the -3, multiply by 1 and get -3, do what it says. 6 minus 3 is 3. 3 times 1 is 3. 9 plus 3 is 12. 12 times 1 is 12. -24 plus 12 is -12. -12 plus 1 is -12, and it gives us the magic 0. So we have just found our first root, and so x equals 1 is a root, which means x minus 1 is a factor. So if I come down here at the bottom where we're keeping track, we have that x equals 1 is a root, and that means, I'm sorry, that I want to do factors as well. So that x minus 1 is a factor. So these are my factors. Now, because we know that's a root, remember that we originally started with 3x to the 4th. So now that means we are down to 3x cubed. So we have reduced our function by 1. And now when we go to divide, we are doing this one. We're not going backwards to x to the 4th, though it technically would work, but you would never end up reducing down to a quadratic. We're trying to get that x cubed to be down to a quadratic. So we're going to now divide into the next level of the factor to see if we can break it down some more. And so I'm going to choose the number 4. So I'm thinking that 1 positive root, but there might be 3 positive roots. So I'm going to divide by 4 to see if there is one. Now, you're sitting there going, but Miss Parker, we know there's not. We know there's not because this was factorable. But I want you to see what you do when, in fact, you find one that is not. So we bring down the -3. It gives us the -12 when you multiply. And I'm going to just walk across because I know you're experts at this because that's what our homework was. Let's see. 4, so that's going to give us 4 times 4 is 16. 8, that's going to give us -96, which when we add those, I believe we get -108, which is not a remainder of 0, which means we don't have a root, but we do have a point on our graph at 4 and -108. So I want to go down here and keep track that even though this is not a root, it's going to help us when we graph because we have a 4, -108. So I don't really want to draw an X through this because it was helpful, but it was not helpful in moving us forward on finding our roots. So that guy was a waste, but we still got a point out of it. So we're back to the same one. So we're not reducing anything. So we're dividing into the exact same thing that we just did. But now let's try the number 2. And when we try the number 2, we bring that down. And now we do get a 0. And so we know x equals 2 is a root, and we know x minus 2 is a factor. So we can do x minus 2 is a factor, and x equals 2 is a root. We started this one off with x to the 3rd, and now that gets us down to x squared. The minute we see x squared, we abandon the guessing game with synthetic division. We come over here and we now have -3x squared minus 3x plus 6 equal to 0. We can try to factor this, which it does not. Well, it might. So we could try to factor this, and it does, because that would be negative 18. Yeah, so you could factor this. However, I'm going to use the quadratic formula just to refresh us. And so we get x equals the opposite of b plus or minus negative 3 squared minus 4 times negative 3 times 6 all over 2 times negative 3. I encourage you to pause. I'm going to jump one step ahead, but you should, because I'm out of room here, but you should end up with 3 plus or minus the square root of 81 over negative 6, which is 3 plus or minus 9 over negative 6. And when you do 3 plus 9 and then 3 minus 9, you should get x equals negative 2 and x equals 1. And so that gives us our two other answers. So we now have one answer here, one answer x equals 2 there, and now we have these two. So we have all four of our units. Let's write them in completely. So we have that another factor would be x plus 2 and x minus 1. Remember, when you put the number over on that side, you have to take the opposite. But it gives you these roots. We know we're done because we were looking for 4 total because of the degree, and we needed only one negative. There could not be more, and we either needed 3 or 1 positive, and we have ourselves 1 negative. I'm sorry, I circled the wrong one. So I'm going to circle the 3 positive, and we had 1 negative. Okay. So we met the Descartes rule of sign, we have 4 roots, and so we know we're done. So just like when you factored and set each one equal to 0, now we just had to do a little more work to get it. Again, we're not going to do this if we know that it can factor. All right, so let's do one that doesn't factor and see how we do on this one. Okay, so make sure they're in order. Once they're in order, identify your P's and your Q's. So your P is going to be negative 4 and your Q is going to be 2. So the factors of P, so P is negative 4. So the factors of that are plus or minus 1, plus or minus 2, plus or minus 4. The Q is a 2. So the factors of that is plus or minus 1, plus or minus 2. So sometimes you hope like, oh, well, there's not very many, so this is going to be easier. And it could be. It just depends how lucky you are at picking. So when we do P's over Q's, again, I'm going to do everything on the top row over 1 and then come back and do over 2. But you can do it any other pattern you want. So we get plus or minus 1, plus or minus 2, plus or minus 4. Then when I go over 2, I get plus or minus 1/2. 2 over 2 gives me 1, which I have, and 4 over 2 gives me 2. So this isn't bad. We have, what, 8 possibilities. Let's check to see how many of the positive ones we're going to use. So if I get my pen to work, if I take I'm going to pause for just a second. Okay, sorry about that. I didn't notice something was on my keyboard and it was just typing all over my screen because something was pushing on my keyboard. So to find how many real roots positive we have to start with our function, and we're going to count the number of sign changes. So see if you can be a step ahead here and tell me how many positive real roots you have. So we have we go from a positive to a negative, which is 1, and then we stay negative the whole time. So we only have one sign change, which guarantees exactly one positive real root. and that may very well come from our list up there. So to do the negative, again, try to be ahead of me. Try to do this yourself. We're plugging in a negative into negative x. Ask yourself whether it makes that term positive or negative. So in the first term, it's going to change it to a negative because a negative 1 cubed is negative 1. The second term, when you square it, it's going to not, it's going to make no difference. Negative 9 times negative x is going to change it to positive 9x, and the negative 4 is not impacted. Here we have no sign change. We do have one here, and we go back here. So we have two sign changes, and they can be 2 or 0 negative real roots. What that means is we're either going to have two negative roots or we're going to have two imaginary roots. And they may or may not be in our list above. So because of that, I strongly encourage us to focus on the positive, because we know that one of them's positive and we have a better chance of finding that one. So as we get ready to synthetically divide using our original function, making sure everything's in order, I'm going to start off with my standard 1. We'll just go down the list. If you have a gut feeling that it might be something else, go down the list as well there. Okay, so I'm going to run through these quickly, but you pause and do each one of these, and hopefully we're good there. So hopefully I don't make a mistake. So this one did not work. So what it does is give me the address of a point, 1, negative 12. So since it didn't work, I'm using the exact same numbers I did before. This time I'm going to try 2. And again, no luck. It gives me a point to negative 10. So I'm racking up the points down here. So the next one I'm going to do is 4. And again, no bobblehead dance. So 472. So I was hoping to not have to do the fraction. I know we love them, but that's okay. We'll do it and we'll see if we get an answer. And it's not looking good. So we are given that 1/2 negative 17/2 is a point on our graph. So we got lots of extra points here. So wait a minute though, what's the issue, right? Because I just said we are guaranteed one positive root, and we just tried every possible positive thing in our list. So where's our positive root? Remember, it doesn't have to be rational, it has to be real. So if it's not in our rational list, it's going to come out of that square root in the quadratic. So what that means is that one of our negative roots has to be the rational one, and that's going to help us. So I wanted to show you that our best laid plan may not work. I'm going to switch colors so I can be over here. I'm still working on the original here, and I just so that I'm not toying with you for too long, let's go ahead and try the negative 1/2. It is a rational negative, so let's see if that one works. If not, we're going to try -1, -2, and -4. So here we go. So 2 times -1/2 is -1, gives me -2. -1/2 times -2 gives me 1, which gives me -8, and a -1/2 of -8 gives me 4, which does give me 0. So x equals -1/2, is a root. We started with x to the third, which means we're now down to x squared. So let me fill in down here that we have a root, x equals negative 1/2, and we know one of our factors is x plus 1/2. And then we're going to go to our quadratic formula to solve this right here, this one factor. So the minute we see x squared, we quit guessing. We take this, set equal to 0. We're going to use our quadratic formula because this one does not factor. And so we get x equals negative b plus or minus the square root of b squared minus 4 times 2 times negative 8 all over 2 times 2 is 4. So I kind of did a little bit in my head there, so slow it down if you need to. So that's going to give me 2 plus or minus 68 over 4. And remember that we have to break down the 68, so 2 plus or minus the square root of 4 times 17 all over 4. The square root of 4 is 2, so 2 plus or minus 2 square roots of 17 over 4. And we can reduce everything by 2, so 1 plus or minus the square root of 17 over 4. And because the square root of 17 is bigger than 1, when we do this minus right here, we're going to get our second negative, and when we do the plus, we're going to get our only positive. And so our three roots are x equals negative 1/2, x equals 1 plus the square root of 17 over 4, and x equals 1 minus the square root of 17 over 4, with the two yellows being our negative answers and the one in between being our positive. To graph these two, remember, take them to decimals. So these two right here are real answers, and this is well, and they're irrational. This one is a real answer but rational. So synthetic division works beautifully when you are quick to pick, but this is why I stressed that you needed to be experts at synthetic division so you could do it really quickly. So even though I had to synthetically divide, 5 times, when I did this problem, really it took about 10 minutes to do the whole problem if you aren't having to really think about that synthetic division. So what I'd like you to do now is focus on being able to find the p's, the q's, the p's over q's, and then determining if they're roots, and being able to identify those roots as factors as well. You technically on this one down here could write it as factored x plus 1/2, and then it gets really messy. X plus, let's see, this would be our negative answer, which is this one, x plus 1 minus square root of 17 over 4. And then x minus, and then the same thing, except it would be the plus. And I'm out of space, but so repeating the same thing with the plus. So those are factors, we just don't typically write it that way, so it's that messy. So work hard for me. I will be on campus Tuesday, Wednesday, Thursday, and we'll see where we are Wednesday. We're shifting to rational equations on Wednesday, but we'll have time to answer questions. I'll be in by 9 Wednesday morning, but I'll also be on campus Tuesday, or feel free to call me or email me throughout the week. So thanks again for your hard work and for understanding, and we'll look forward to seeing you in class on Wednesday.